In this video, I'm going to be doing calculations of how to calculate current and effective resistance around a given circuit. Now, if we remind ourselves from the previous video that let's say if we have the resistors connected in series, we form what we call a voltage divider, and in power connection we form a current divider. Now that in series connection, if we have two resistors, and this is resistor 1 connected to resistor 2, let's say this is R1, this is R2, so we form what we call a voltage divider. Now let's say the PD across R1 is V1, right? V1, and the PD across V2, across R2 is V2 from this point. Now, when we are in series connection, let's say we want to get the PD across one of the resistors. Let's say the PD across R1 would be equals to that my R1, it would be V1 equals to, I would say that this is R1 all over R1 plus R2, then close this, multiplied by the total voltage from the source. And also, let's say if we are to get that of 2 R2, which would be V2 equals to R2 all over R1 plus R2, right? Then multiplied by V, right? And also, when we are in power connection and we have a circuit of this kind, we have our resistor R1 at this point that current is flowing through. And here also, consider that current was flowing through. So here, current will divide. We shall have I1, and also the one that will go through R2 will be I2, and then the current combines at one point, of which they say this is the point, to form, let's say this point we shall have I1 plus I2 will give us I again, the total current, right? Now, when we are in power connection, we form a current divider. And when we are to get current through any of the resistors, we say that, let's say I1, which would be equals to R2 all over R1 plus R2 plus this multiplied by the total current, right? And then if we are to get that of, let's say, of resistor 2, which would be I2, that would be equals to, would have R1 over R1 plus R2 multiplied by total current, right? Now, these let's say the formulas that we generated from the previous video, that if you are to get current in power connection of one of the resistors, this is what you would follow, right? And also in series connection, that we form what to call a voltage divider. And so if you're to get PD across any of the resistors, this is what you follow, right? Now, also we know that, now these are just basics, that in series connection, we know that total resistance would be equals to R1 plus R2. Now, depending on the number of resistors that you have that are connected in series. Now, also in parallel connection, this is in series. Now, in parallel connection, we shall be having that the total resistance R total equals to R1, R2 over R1 plus R2, right? Now keep in mind, we're going to use this in circuit analysis. Consider that we have a circuit of this kind, that we have a voltage source and we have a resistor that's connected. This is R, and this point connected to this, right? Now, current flows from positive to negative, right? Of which we consider that as potential drop. That as current flows from here, that the potential at this point is greater than the potential at this point, right? So, current flows through this, but as it reaches here, the potential drops to 0, right? Then the potential rises from the negative to the positive. And therefore, in consideration from Ohm's law, we know that V is equals to IR, right? So out of that, that means that if I'm to get one of them that's missing, I just make, let's say, one of them the subject. For example, if I'm interested in resistance, V over I would give me R. And if I'm interested in current, I would say that V over R would be equals to the current. Now, let's start right away with some examples. We have our resistor here of 2 ohms connected to 3 ohm resistor, and we have let's say we have the 2 ohm resistor, and this is connected to a voltage source of 8 volts, positive, negative, and at this point, right? Now, we know that current is going to flow from positive, right? Taking that direction. But if you look at the arrangement of the resistors, 2, 3, and 2, they're in series because there is no point where current is divided, right? And therefore, for total resistance, since we are in series connection, total resistance should be equals to, we shall have 2 plus 3 plus 2, of which this would give us 7 ohms, right? But then to get current, we know that from Ohm's law that V would be equals to IR, right? And then we have got a total resistance, which is 7, right? So that means that this is the same as having for current to be equals to V all over RT. So this current would be equals to, shall be having 8 volts all over 7. And therefore, our answer will be in amps. 8 divided by 7. This would give me 1.143 amps, right? So, this is the total current that's flowing throughout this circuit. But since the resistors are in series, that means that the current through them is the same, right? Now, let's confirm. The current through the 2 ohm resistor, I, is equals to 1.143 amps, right? So now considering the current flowing through the 2, 3, and 2 resistors. So you find that if you look at this, you have, let's say, V equals to IR, right? Which in this case we are having PD across the 2 resistor. Shall have V for the 2 resistor. This will be equals to 1.143 times 2. And so this would give me 2.286 volts, right? Now, also the PD across the 3 resistor shall be having the 3 resistor. This would be equals to 3 times 1.143. So I'll be having 3 times 1.143, 3.429 volts. And also the PD across the 2 resistor. This is the same as this. The 2 resistor would be equals to 2.286 volts. Now, if you sum up all the PDs, they have to give you the same volts, like the one at the voltage source. Now, let's add up and see that V will be equals to 2.286. Actually, this is times 2 because of this and this. So times 2 plus we're having 3.429, right? So plus 3.429 plus 2.286 times 2. 8.001, which is approximately 8 volts, right? That means that we are on track. So that's how, let's say, I would calculate, let's say, the current, the PD across each resistor, let's say, for this circuit. Let's try another example that I'm having a 1 resistor, have the 2 resistor, have another 1 resistor, have another, this is a 2 resistor. They both all have a 16 volt source, right? Now, this is 16 volts. Now, if you look at this, current will flow from positive. So we have our I here, which will be a total current into the circuit, right? Now that current comes and divides here. We shall have here I1. Here we shall be having I2, right? Because at this node, that's where current splits into I1 and I2. Now let's do the circuit analysis. That if you look at the 2 resistor and the 1 resistor, now these ones are in parallel connection. Now let's calculate the resistance. The resistance in parallel connection, we shall be having 2 times 1 all over 2 plus 1. This is going to give us 2 all over 3 ohms in parallel connection. Now, in the same way, if you look at now, if we redraw this circuit, I am going to remove this because now we have calculated here, and the resistance here, the resistance here is no longer 2. Let's replace this by 2 out of 3 ohms, right? Now, if we look at this 2 and 2 over 3 and 1 are now in series. So that means that the resistance now, this will be total resistance, would be equals to, we shall be having 1 plus 2 over 3 plus 2, right? This would give me, I'll be having here, this is 3 plus 2 over 3, giving us something that's going to be, shall be having 9 plus 2 over 3, giving us 11 over 3, right? So, in decimals, b equals to, shall be having 3.667 ohms, right? Now, this is the total resistance. That means that now we can get total current. Current, we know that V is equals to IR. That means that I equals to the voltage, which is 16, divided by the total resistance, 3.667, right? So, 16 divided by 3.667, giving us 4.363. This will be in amps, right? Now, having got that, we know that now this is the total current into the circuit from the voltage source. Now, out of that, when I'm to do the circuit analysis again, now the current that's going throughout the whole circuit from this point, let's say our I, which is equals to 4.363, this will be in amps. Now, that current divided into, we had here our I1, this was I2, right? Now, the current that goes through this, I have to get the current through the 2 ohm resistor and the 1 ohm resistor, right? And afterwards, we are going to make confirmations. Therefore, for me to get the current through the 2 ohm resistor, here I can say that I1 equals to, shall be having 1 all over, right? 2 plus 1 multiplied by the current into that branch, of which this like that's coming from another branch, which is 4.363, right? Over 3 multiplied by that 4.363. 1 divided by 3 times 4.363. I am getting 1.454 amps in this case, right? So if I go there, this like for I1, that means I can get I2. For me to get I2, this will be equals to the total current, which is 4.363 minus 1.454, right? So in this case, I'm going to be getting 363 minus 1.454, giving me 2.909 amps, right? So now having got that, I can know the potential at different nodes and the potential drop across a resistor, right? So out of that, we know that this was I1, right? We got I2, which was this is 2.909 amps, and the total one. So now I can remove this. Potential at this point right here has to be 0 volts, right? Now let's confirm that potential difference across this resistor, right? Let's say V across the 1 ohm resistor would be equals to, but I know that this is the potential at this point initially is 16 volts, right? Potential difference across the 1 ohm resistor will be, let's say, 1 times total current rate, which is 4.363. So that is, we're having 4.363, right? I mean that the potential drops by 4.363. That means that 16 minus 4.363, giving me 11.637 volts. This point is also at the same potential because there is no resistor at that point where, let's say, the potential would drop. So that means that here we're having also 11.637 volts. They are at the same potential. Also, the potential drop across this resistor, right? Let's say V of the 2 ohm resistor would be equals to, you're going to have 2 times the current that goes through it, which is I1, and now I1 was 1.454, right? So it is 2 times 1.454, giving me 2.908 volts, right? So that means that at this point we're having our 11.637 minus 2.908, giving me 8.729 volts at that point. Potential at this point is this, right? Now let's get the potential at this point, right? Now these points are supposed to have the same potential because there's no resistor in between here that would cause a potential drop. So let's say 11, this is 11. The current that goes through the 1 ohm resistor is I2, right? So I2 is this times 1, you're getting 2.909, right? So that means that, of course, this resistor, we are going to have 11.637 minus 2.909, right? Giving us 8.728, right? Relatively, let's say if you look at the potential relatively, it's almost the same, right? So, let's get the potential, let's say the PD across this, of which we shall be having, the current that goes through the 2 ohm resistor at this point is as a result of, let's say, I1 plus I2, because as this comes and this, they combine at this point, right? That this current is as a result of I1 plus I2, which would give us something that would be, we're going to have I1, which is 2.909 plus 1.454, right? So that means that we shall be having 4.363 amps through the 2 ohm resistor. That means that let's say the PD would be, shall be having V is equals to the 2 ohm resistor. The PD across it would be of the 2 ohm resistor would be equals to 2 into 4.363 3, right? So that means that 2 times that shall be having 8.726 volts, right? Now you find that the PD across this resistor is 8.726. Now if you subtract this 8.729 minus 8.726 is relatively 0, right? So you find that that's why potential drops from the positive to the negative, right? And then raises from the negative to the positive. So that's it for this example. Let's try one more example. Let's consider this circuit. We're having multiple resistors. It's saying, now, if we are to calculate the effective resistance in this circuit, now, I would, let's say, prefer whenever you calculate the resistance in a given, let's say, in a given branch, you redraw the, let's say, the remaining part of the circuit, right? For easy follow up. Now, if you look at, let's say, if I start from here, look at the 6 and the 3 are in series, right? Now, let's first resolve that and then we move to the next part. So, in series, if you add 3 plus 6, we are having, let's say here, this would be 9, right? So that means that here we're having 9. That means we can replace the whole of this by 9, right? So let's have it. I can remove this and say that I'm going to be having something of this sort. Here we are having the 2 ohm. Here we're having the 3 ohm. This is connected to 4, right? And then this is connected to the 5 ohm resistor. This is connected to the 2 ohm resistor, right? And then the 2 ohm branches to the 1 ohm resistor. And then this here, replace the whole of this by, let's say we are having the 9 ohm resistor, right? So at the end of the day, if you combine this in between here, we are having, this is the 2 ohm resistor, which is connected to this, and then the whole of this like this. Now also here, we are having this connected here and to the rest part of the circuit. Here we're having the voltage source. Now, this 9 is in parallel with the 1 ohm resistor, of which here we're going to say that in power connection, of which the resistance in power connection, we normally have something that is equal to, so we shall be having, this will be 9 times 1 over 10, right? Because this would be 10, so giving us 9 all over 10, right? So this one is like having 0.9 ohms. It means that I'm going to replace, let's say, where there's 1 and 9 by a 0.9 ohm resistor, right? If I redraw this, that means I'm going to be removing this, and so if we remove this and this one, right? So this is, we are having 0.9 ohm resistor, right? Now, if you look at 2, 0, 9, and 2 ohm resistor, they are in series, right? So that means that since they are in series, but in parallel with the 5 ohm resistor, and therefore, that means that in series connection, I'm having resistance here in series connection, we are going to have 2 plus 0.9 plus 2, right? So that means that we are having 4.9 ohms, right? That means that I'm to replace the whole of these with, let's say, 4.9, right? So that means that if I redraw this, therefore, I replace the whole of these by a 4.9 ohm resistor. Now, if you look at the 5 and the 4.9 ohm resistor, they are in parallel connection. Therefore, resistance in parallel connection will be equals to, we would have 4.9 times 5 all over 4.9 plus 5. In this case, plus 5. And this would be 4.9 times 5 all over 4.9 plus 5. And this would give me 2.475 ohms, right? Now, the whole of the power connection. Now, that means that I'm going to remove the whole of this and replace this resistor with a 2.475 ohm resistor, right? Now, if we are to replace this and this by a 2.475 ohm resistor. If you look at this, the 4 ohm resistor and the 2.475 ohm resistor are in series, but in power with the 3 ohm resistor. And therefore, our resistance will be equals to, shall have, right, 3 into 4 plus 2.475, right? Then all over, we are going to have 3 plus 4 plus 2.475, right? Now, if you work out this, you're going to have something of 3 into, you're having 4 plus 2.475. We're having 19.425 divided by 3 plus 4 plus 2.475, right? And overall, at this point would get 2.050 ohms, right? Now, having got that, whatever that we have got here, we are going to replace the whole of this, right? So, and therefore, would replace the whole of this. And this 3 would replace it by 2.050 ohms, right? Now, here, let's say, let's say our voltage source, which was 24 volts, positive, minus here, at our 24 volt source, right? Now here, the total resistance, our total, equals to 2.050 plus the 2, giving us 4.050 ohms, right? That means that this can enable us to get the total current that was from the voltage source. Then current, we know that I equals to, we're having, let's say our 24, divide this by 4.050, right? So this should be equals to 5.926 amps, right? Now, this is the total current that's from the source. Now, let's use this current to get, let's say, the current through different resistors. And now, as we know that the total current from the source, this was 24, of which that would be our I, is equals to 5.926 amps, right? Now that's the current through the 2 ohm resistor. Now that current goes on splitting. Let's say we had here, this is we had here, this is going to be I1, I2. Also here, this would be I2, I3. This would be I4, and then this would be I5. This would be I6, right? Now we can get all these currents, right? Now the current through the 3 ohm resistor. Remember, the 3 ohm resistor is in parallel with the whole of this up to here, right? So if you look at the 3 is in parallel with this. But let's say 3 is in parallel with 3 plus 0.475, right? So that means that for me, if I get the sum of this, of which 4 plus that, yeah, the 3 ohm resistor, right, is in parallel with 4 plus 2.475, right? These are being ohms. So that means the 3 ohm resistor is in parallel with 6.475 ohm resistor, right? Because that resistor replaced the whole of this from here, from here up to here, right? So for me to get the current through the 3 ohm resistor, I know that that would be I1. That means that I1 would be equals to, now that's we are having 6.475 divided by 3 plus this, we're going to have 9.475 times the current that's coming from 2, right? With that would be 5.926, right? So the current would be 4.050. This would be amps, right? Now that's I1. Now let's get I2, of which we know that for us to get I2, this would be equals to, we are going to have total current, which is 5.926 minus 4.050, right? 1.876 amps, right? Now that's the current that's going through the 4 ohm resistor, right? At the same case, that means that I can get I3, then afterwards I2 minus I3 to give me I4, right? But if you look at now, the 5 ohm resistor is in parallel with the whole of this, right? Now, out of that, let's try to get I3. But we know that I3, let's remember, the 5 ohm resistor is in parallel with 4.9 ohm resistor, which replaced the other part of the circuit, right? So this is 4.9 ohm resistor. That means that out of that, so we know that this 5 is in parallel with 4.9 ohm resistor. That means that for us to get I3, we shall say that I3 is equals to 4.9 divided by 4.9 plus 5 multiplied by the current that's coming into that, which is I2. And we got our I2 as 1.876, right? Therefore, if you work out, and so here we would get 0.929 amps, right? Now, this is I3. Now, for us to get I4, in this case, we have to say that it is I2 minus I3, right? Which our I2 in this case was 1.8. That means that here, I4 will be equals to, we're going to have 1.876 minus 0.929, right? Give us 0.947 amps, right? Now, also, we know that since we have got I4, we can get the current through the 1 ohm resistor, which would be the I5, right? But then the I5 go through the 1 ohm resistor. The 1 ohm resistor is in parallel with the 9 ohm resistor, right? So that means that for us to get I5, that our I5 equals to 9 all over, you're going to get, this is, we had something that was 1 plus 9, right? So that would be 10. Now, times the current that's coming from this part, which is I4, right? So that's times 0.947. So we shall be getting to be equals to 0.852 amps, right? That means that in the same case, we can get I6, right? So our I6 will be equals to, you're going to have 0.947, right? Minus 0.852. So in this case, we shall be having 0.095 amps in this case. So out of that, that would be our I6, right? The current that's going through the 3 and the 6 ohm resistor. Now, let's try to confirm our answers, and let's say using potentials at different nodes. We know that different nodes are at different potentials, right? Now, the potential at this point is 24 volts, right? Now, previously we knew that, let's say the current that's going through the 2 ohm resistor, this is, let's say, 5.926, right? Now, the potential drop, right? The potential drops by, let's say, 5.926 times 2, right? To give us the potential at that point, right? So let's try to get the potential at this point, which would be equals to, we shall be having 2 times 5.926, giving us 11.852, right? Now, our 24 minus this answer, which would give us 12.148, right? So we shall be having 12.18. At this point, we shall be having 12.148 volts at that point. Now, current that went through the 4 ohm resistor, we had, let's say, which was I2, right? Now, the PD across the 4 ohm resistor is a 4 times our I2, of which our I2, we got something that was 1.8876. So then we're having our current that goes through the 4 ohm resistor, which is I2, and therefore shall be having 4 times I2, which is 1.876, giving us 7.504, right? Now, remember the potential at this point, we got something that was, we had 12.148, right? So we subtract this 12.148. So the potential at this point will be 4.644 volts, right? At this point, right? Now, let's get the potential at this point. We know that, let's say, a current that was through the 2 ohm resistor, which is this, was the I4, right? The I4, of which our I4 was 0.9947. So 0.947 now times the 2, giving us 1.894. So 4.644 minus this shall be getting 2.750, right? This will be in volts, right? So that's the potential at that point. But at this point, now also, the potential at this point also varies, right? So let's get the potential at this point also. Now the 3 ohm resistor, let's say the current that went through it was the I6, of which our I6 in this case was 0.095. So our 0.095 times that was our 3, giving us 0.285 volts, right? But then at this point, you're going to subtract this, let's say 2.750 minus, so 2.750 minus the answer 2.465 volts at that point. Then the same current went through the 6 ohm resistor, right? So that means that 6 times the same current. At this point, we had 6. I6 went also through the 6 ohm resistor. So it is, we're having our 6 times that current, which is I6, and our I6 was 0.095, right? So we are getting 0.57. Now that 0.57, 2.465 minus 0.57 shall be having 1.895 volts, right? Now, there's current that went through the 1 ohm resistor. If you look from this diagram, we had, let's say, I5 went through the 1 ohm resistor. So that means that the current that was I5, so 0.85 5, 2 times 1, we still have that, right? But then if you look at this, the potential at this point was 2.750, right? 2.750 minus 0.852, we shall be getting, at this point, we shall be getting 1.898 volts, right? But now, the current that's going to go through the 2 ohm resistor, right? If you look from this diagram, that I5 will combine with I6 at this point, right? And therefore, we shall be having, let's say, I5 plus I6 going through the 2 ohm resistor. That means that the current through the 2 ohm resistor, if we are to get the PD, we are going to add I5 plus I6, right? Which our I5 in this case was 0.852, 0.852 plus then our I6, which was 0.095. And so if I add I5 plus I6, this will give me, I'm going to have 0.947 amps, right? But that's the current that's going through the 2 ohm resistor. So that means that the PD across that resistor equals to 2 times 0.947, right? And this would give me 1.894 volts, right? But then I know that the PD, let's say from here to here, right? Let's say the PD, let's say across this resistor is 1.894. Now, I want to get the potential at this point, right? Potential at that point, 1.898. So that means that minus, right? 1.894. So which would be, let's say, approximate to 0, right? So that means that this is, I'm having 0.00, I would consider this, let's say, a 4, right? But approximately it is a 0, right? Now, also here, I know that they say the current, now the whole of this is, let's say, like up to here. Let's say approximates to 0 volts, right? Because that's like, if I round off this, almost 0, right? So all of this is to 0 potential. Now, let's say the current now, let's say here, if you look at this, say, let's get the potential at this point is this, through this, and that, right? Now let's get, let's say, using this, that if we have 4.644, the current that went through 5 ohm resistor, right, is, if you look from this, the 5 ohm resistor was I3, right? So our I3 was 0.929, right? So if we have our 0.929, right, times 5, 929, and then times 5, that this would give us 4.645, right? So you find that 4.65, but if you check in the second, it gives me almost the same potential as that at this point right here, right? The potential is the same. So if I subtract, it gives me 0.000. Let's say like that, right? So if we approximate it, it's still 0. So at this point, let's find out whether it gives us approximates also to 0. So if I have 12, the current that went through the 3 ohm resistor from this previous diagram, the 3 was I1, which is 4.050 times the resistor, which is 3, right? 3, that would give me 12.15, right? But if you check the potential at that point is 12.1485. Now, due to rounding off, that's why we can approximate this also to be 0, right? So if you subtract 12.14, 12.1485 minus 12.15, I would still get 0.0015. If you approximate that, it gives us still the 0. So thank you for watching. See you in the next video.